Hello IB. Today we're looking at this next section on integration by substitution in 18G. What we want to look at is where we're going to get one step further on our integration. So at the moment we've looked at where we've got, they're basically composite functions, where we have a function, in this case a linear function, inside a bigger function, a squared or quadratic function. We want to aim to where we have things that we're trying to integrate that have got a whole lot of x's being multiplied. So we want to see how do we do things like that, because we talked about not having a product rule as such. So if we come back to here and just think about what our process was, we identified that here we've got our small function inside here. And we said when we just normally differentiate that and we get 2x to the 5th plus 5 at least, and we do times 3 at the front, and then we multiply by our 2, and that gives us our 6, and the power of 2 up here. So we're getting 6, 2x plus 5 squared. So that means if I wanted just to integrate that, 6 brackets 2x plus 5 all squared, we know that comes to exactly 2x plus 5 cubed plus c. And then we went, well, what if I just want to integrate 2x plus 5 squared and I don't have that 6 at the front? We could easily, with this statement, this equality here, we can just simply go, well, let's just multiply this by 1/6 and this times 1/6. So that's 6, because it's just a constant, that can move outside your integration. That's one of the rules of integration that we had. So now the 1/6 will cancel with that, and so we can come up with our answer of 1/6 2x plus 5 all cubed plus c. And we saw that that 6 actually came from the 2 times 3. And the 2 here was the derivative of this linear term. So the derivative of this term in here was 2, the coefficient of x. The 5 just drops out. The 3 has come from our power. So that's part of our rule of integration. So now let's go to something more complicated. If we've got inside our composite function, we have, in this case, not a linear function, but we now have a quadratic inside a cubic. So we talked about f of g and all those things, so we can talk about a function in a function. If we differentiate this, then we're going to have x squared plus 5x, and our first step is to bring our 3 down the front, subtract 1, so that's now squared. Now we multiply by the derivative of this, of our term inside, and that becomes 2x plus 5. So that means if I want to integrate 3 times x squared plus 5x all squared times 2x plus 5 dx, then I can say my answer is x squared plus 5x all to the power of 3 plus c. But the most I can do to change this is I could take the 3 out of here by multiplying both sides by 1/3. I can do that just with numbers, all right? So I could say the derivative of that is 1/3 of this, 5x cubed plus c, or plus d, whichever. But I needed both those terms there. I can't multiply this by x's or anything. So if I just had this inside part of my function, If this bit didn't exist here, I couldn't integrate it. I can't multiply the front by 2x plus 5. That's not one of the rules we do. So what we want to be able to do is, when we've got something like this set up, to be able to recognise it and then to be able to integrate it, and it's a nice simple integration. So what we're going to do is call this inside part u. So this is going to be our u. What's the function inside another function? And it works if it's linear or whatever. This could be a sine or a cos or an exponential, whatever it is. If we have some internal function, x squared in this case, x squared plus 5x, then we can differentiate that. So this is now u in terms of x. So u dash x, or du dx, is now going to be 2x plus 5. So what we want to be able to do is recognise that this here is the derivative of that. So if you differentiate this and get that term, then you're on the track to doing integration by substitution. So now if we write our function in terms of u, so this is u, what are we doing to u? We are squaring it. So f of u is u squared. What we can now do is basically swap everything over in our equation to write something in terms of u. So now we've got our integral of, this is u, all right? So we're now going to see how, x squared plus 5x is u. So we can now write this as u squared. 2x plus 5 is the same as du dx. So this, run out of space here. This little expression here, we can swap with du dx. So we write in here du dx. And then our last part here, we still write our dx. So we're trying to integrate with respect to x. But what we've effectively done by substituting our little linear term here with u, we now don't have any x's in this expression. So we've talked about this, it's sort of a fraction but not a fraction. Because it's du dx times dx, these are all multiplied together. So everything here is just multiplied. It's as if they cancel. I'm not going to show it cancelling because it's not really a fraction, but it's as if they're cancelling. It's like going, I want to turn Aussie into US dollars and then US dollars into pounds sterling or whatever. It's the same as going from Aussie to pounds, but we're going via something else. So if we want to integrate with respect to x, we've sort of got to go via du and then to dx. So now we can write this as u squared du. So we want to integrate that with respect to u. And that means we end up with u cubed. So remember, the power goes up, divide by the new power, plus c. And then we go, well, I know what u is. Put our third out the front. What was our u? Our u was x squared plus 5x. So now we substitute back our x squared plus 5x plus c to the power of 3. All right, so we've got a system now, a mathematical way of showing why we can integrate where that third comes from. So we don't have to sort of guess about what to put out the front here. We've got a way of being able to formally integrate when we've got two functions being multiplied and one is the derivative of the function that's inside another function. So this here is like a composite function. And this part here is the derivative. So So that's what you're looking for, a function inside a function and it multiplied by its derivative. So now when we integrate f of u du, that gives that primitive function of u, which is what this is here. So let's do, let me just see. Right, so here a similar example. We'll leave you to do this one at home. So let's have a quick look. We've got 3x squared minus x all to the power of 4 times 6x minus 1. So the question is, look at the two things being multiplied. We've got this term inside a bracket and that term inside. Can you recognise that this is the derivative of that? So if you differentiate 3x squared minus x, you'll get 6x minus 1. So that means this is our u, so our u is 3x squared minus x. Du dx is 6x minus 1. So now you can just substitute in our u, the du dx, and integrate. So when you see two functions being multiplied together, ask yourself, is one of them the derivative of the other? This one here, again, have a look and go, right, two things being multiplied together. You've got this inside a square root, and this. Is one of these a derivative of the other? Yes, because x cubed plus 2x differentiates to give 3x plus 2. So our u function is x cubed plus 2x. Our derivative function will be 3x squared plus 2. So we'll be able to substitute in. So your first step is always going to be rewriting this. Remember, if it's a square root, then that's the same as u to the half. Then you'll go du dx for this next part, times, you don't need to put the times, dx. All right, we're going to leave you to work on that one. We'll go through that in class. This one, again, have a look. Sometimes you might need to think about it and split it to see what's happening. So you've got a 2x times 1 over x squared plus 1. All right, all of these are multiplied, dx. So here you've got something multiplied, but it's in the denominator. It's to the power of minus 1. Hopefully that will ring a bell if it's 1 over. If this is x squared plus 1, the derivative of that is our 2x. So good, we've got those two, there's two a part of our equation. So we can now write, we have the integral of du dx times 1 over u dx. So we have the integral here of 1 over u du. What's the integral of 1 over u? Hopefully you recognise that by now. So we've got the natural log of u plus c. And what was our u? X squared plus 1. So that will equal the natural log of, put it in brackets, x squared plus 1 plus c. Normally we've written that with our absolute value signs. Do we need absolute value signs with x squared plus 1? That's a good question. X squared plus 1, if you square any number, it's going to be positive and you add 1 to it. So that will always be greater than 0. Oops. So you can put the absolute value signs, it won't be wrong, but it will always be greater than 0. This one, let's have a quick go at this one because it's slightly different. Here again, we've got two things being multiplied. We've got this and a function, and there's our function in the function. This is our composite function. So if we make our substitution 1 minus x squared, and we have an x here. Now when we differentiate this, we get minus 2x. Do we have a minus 2x here? No, we don't. So what we can actually do, we can treat this like a little equation. Let's divide both sides by minus 2. So that's the same as multiplying by minus a half. Okay, we're going to divide both sides by minus 2. So in other words, we can say that x equals minus a half du dx. So now when we do our substitution, we get the integral of minus a half. So our x is swapping for all of that. Minus a half du dx, e to the u, because there's our u, our 1 minus x squared, du. Doesn't matter these aren't next to each other at the beginning. The minus a half, that's just a constant, so we can leave that out the front. Integral of e to the u, and then du dx times du. Oh, mistake, did you spot that? You need that to be an x. So du dx times dx gives us du. Now we can integrate minus a half. What's the integral of e to the u? Is e to the u plus our constant of integration. And our u was 1 minus x squared. So it equals minus a half e to the 1 minus x squared plus c. All right, so there's some others we'll do in class. We'll look at those. But if you can just at this point make sure you understand what's happening right back up at square one when we've got a linear, what we're doing there, but then how we can use a substitution to swap things that are looking quite complicated, and that's a method of working through and choosing, selecting the composite function, what's the inside function inside there, take the derivative and then swap it out in each part of your integral statement. So thanks for listening, and we'll keep going with this in class. Bye for now.